Good afternoon, everyone. Am I audible?
Yes.
Okay, thank you. So it's 2 o'clock, so we will start. Uh, let's see how many participants are there. So 12 people have joined, but okay. I mean, we can wait for 3, 4 minutes, and then we will start them. Okay, we will start. So I'll just put up my slides. Are the slides visible? Okay. So welcome to the second day of this course. Yesterday we had discussed about the motivation for parallel programming and why is it needed. Okay, yeah. Then we discussed something called the Moore's law and how does it help us in the quest for parallel programming. We also talked about Amdahl's law, which shows us that actually increasing the number of cores without any other thought does not actually make sense, and there is a limit to the speed up we can achieve. That's what Amdahl's law tells us. And also, we looked at the various types of hardware elements for parallel programming. By the way, am I audible? I
Yes.
Yes.
okay. Thank you.
Yes.
All right. So, okay, we will proceed with this. So today we will see how we will be programming such devices, the type of devices we saw yesterday, all the multi-core CPUs, GPUs, and things like that. How can we program them? So we have to use them somehow. It does not make sense just to buy the hardware. You cannot simply put a serial code into a GPU or a multi-core CPU system and expect it to run on all the cores. You have to program it a bit slightly differently. So as I said, how to program depends on what hardware you are targeting. The procedure for parallelization will be slightly different if you have a multi-core CPU, will be slightly again different if you have a GPU, will be very different if you have an FPGA and things like that. So it depends totally on the hardware you are trying to program for. So it is hardware dependent. It also depends on the type of problem to be solved. As we saw yesterday, all problems are not parallelizable. So you cannot try and parallelize a problem which is not parallelizable. Let's say a problem is serial, like it can only be solved if solved serially. Let's say the problem is dependent on the previous step. There is some step which has to be performed. After that only you can do the other step. That sort of a problem cannot be parallelized. And what we learn, like from experience, we have seen is data management is king. Like most important part of any parallel programming framework, a program, whatever you want to do, you have to be very careful about how you are managing data. Why is this? Because we are going to have multiple CPUs or multiple cores solving a type of problem which will be working on different types of data. So especially in cases which have separate memory, the type of thing I will come to a bit later, data management becomes very important. Okay, so where is data stored? Data is generally stored in memory. So for one system, it is probably your RAM. For GPUs, it will have some, GPU will also have some internal memory. So data is stored in that memory. And therefore, we have to look into some of these memory models. By what I mean by memory models, like there is a hardware part of it, like how the memory is constructed using flash, NAND flash and things like that. But to software, how does the memory look? That is given by the memory models. So there are mainly three major models. So first is, the first two popular types are the shared and distributed. I'll come to every one of them separately. And since this is a GPU programming class, we have a heterogeneous memory model. We will come to it also. And generally, clusters and supercomputers, which we have everywhere around us, are generally a combination of all of these three. So there are mainly three major sort of models of memory, and all practical supercomputers what are built are generally a combination of all three of them. So we will go on to shared memory model. So this is a sort of a diagram which I have made to describe a shared memory model. What does it show? So this depicts, if you see, the green parts I have written core 1, core 2, core 3, core 4. And there are four such things which have a yellow part which says memory. So if you go back to the example we discussed the previous day, there was a quad socket CPU motherboard I had shown, a sort of a motherboard which can take four CPUs in a single motherboard. This example might as well have been given using two such CPUs. Then in that case, there would have been two such cores, two such things like this with memory and four cores. I am assuming per CPU, there are four cores. Just for the sake of explanation, I am assuming per CPU, there are four cores. And in real life, these are much more, 6, 8, 10, 12. But for example, I'm considering this. And it has some RAM attached to it. That is our memory. So if you remember and go back to the slide we had previous day, you would have seen beside every socket, each CPU goes into a socket. Beside every socket, there was a few RAM slots. Generally, those RAM slots are connected to the most adjacent CPU, which is there. And each CPU has some cores like this. Again, I told yesterday that all the RAM which is there in that, let's say in that four socket machine, all the four CPUs can directly access the memory in each and every memory stick or RAM. It does not matter if your memory is here and this core has to access it, it can access it. But there is slight difference. So if you look at the diagram here, how it is made, you will see that the memory is sort of shown as directly attached to these four cores. Like it is here, it is directly attached. What do I mean by this is, these four cores have fast and direct access to this memory. Since it is in hardware, it is put right adjacent to it, and the memory controller for this memory's RAM is directly embedded into the first CPU, which is this one. Same thing goes for this, this, and this, all three. Okay. So similarly, if in this case, the core 1, 2, 3, and 4, this can directly access the memory here. But let's say this core 3 in the bottom left corner has to access some variable which is stored in the memory in the top right corner. It can access that, but it has to go through something called an interconnect. Different companies have different vendors, like Intel and everything has different names for this, but it is a sort of an interconnect, which is technically a bit slower than what you can have if you have direct access. Like the core 1 here, which I am pointing to here, will have faster access to this memory, than the core one, which is in the top bottom left corner of it, because it has to go through an extra interconnect layer. Why is this called a shared memory model? Because as we discussed previously, all the memory, let's say there are 4 memory sticks in this diagram, can be accessed by all the 12 cores, all the 16 cores, sorry, in this thing, in this one model, in this one node. So it is called a shared memory model. Why? Because all the cores have access to all the memory. Each individual processor can have multiple cores and associated memory controllers. As I said, each individual, this green part is each individual processor and can have multiple cores, and they have the associated memory controllers. They are connected by an interconnect, as I have shown here in blue, such that the cross communication delay is more than the direct communication cost, but still it is quite fast. This is particularly called, this is a term, technical term called NUMA, or non-uniform memory access. Why is it non-uniform? Because different CPUs, depending on which processor it is on, has different access times. Therefore, it is called non-uniform memory access. So you might ask the question, why is it made like this? I will come back to it. And the other question is what is called memory, how is memory mapped? Sorry, somebody is adding. Yeah. So that follows something called first touch policy. I'll explain what that is. Let's say core 1 has to assign some memory. Let's say it has to assign some array or some variable. In that, whatever it is connected to this memory, right, on the right hand side. So first touch says that the thread which is executing on core 1 will assign memory into this part of it. So whichever is getting first access to it will be assigned to that part of the memory. Why is this done? Again, it comes back to the NUMA. It will try to allocate that memory or that variable in the memory nearest to it. So you might ask the question, why are we creating something like this, which is a bit complicated? You have to have an interconnect and then some connection with memory and things like that. Why not make it something like this? This is also sometimes used. This is called UMA, or Unified Memory Access. And what it is like, all the cores, like over here what we had, some 16 cores were there. They are connected to separate memories. Over here, I have taken an 8-core example, and it is connected directly to the memory here. Can anybody say, like, guess why this is done? Why this is not generally done in case of multi-processor systems? Can anybody guess?
Because each core has to go through this interconnect, where in the previous thing only a portion of the cores have to go through the interconnect. Here,
So
going through interconnect is compulsory.
yeah, so what happens, like, if every core has to go through one interconnect, what is the issue?
There will be bottlenecks, right? Only
Correct.
at one time, only one thing can go.
Yeah, correct. So this interconnect may get saturated and it might become a bottleneck. So let's say 1, 2, 3, like all of the cores are trying to access the same memory. It might bottleneck up in this interconnect. So generally, if you have multiple sockets, this is what is followed. Okay. So this is what is about the shared memory model. So is there any questions regarding this before I move on to the other things? Does anyone have any questions?
Regarding the bottleneck of interconnect in the unified memory model,
Yeah.
wouldn't it make sense to just create one interconnect between each core and memory?
Wouldn't it make sense to have one interconnect between each
For
core?
each core, like you said, like the problem is that there's a bottleneck for one interconnect, right? Like
Yes.
just create lots of interconnect.
Yes. So I guess that can be done. I am not sure about it, but uh, can memory access be done in parallel? That would be the question. I am not sure. I'll have to check up. I'll check up and let you know. It's a good question. Does anyone else have an idea about that? Okay, I'll check this up and let you know. Okay, I will move on to the distributed memory model. So we had one such node in the shared memory model. We had discussed the previous day, this would somewhat represent something like a single execution, a single server node in your cluster. So yeah, so this is one full rack which has 4 CPUs and it has its own memory and everything like that. Now in the distributed memory model, what happens is there are many such nodes. So there is a node here, a node here, a node here. There are like this many nodes which are connected using some sort of networking. So that is the green. This is this interconnect is different from this interconnect which is given here, which is internal and this is external. This interconnect is different. But this is also quite fast, not as fast as the interconnect in the CPU, but this is also quite a fast interconnect. And why is this sort of a model necessary? This sort of a model is necessary because, as we saw yesterday, you can have at most 4 CPUs in a single socket, in a single server node. That is also quite expensive. So if you have some bigger models you want to run, or if you want to store a large data set into your memory, maybe your memory in a single node is not enough. So do that sort of a processing and that sort of a computation, you will need multiple such nodes which are to be connected so that each node can process in parallel some part of the problem, which is not possible in a single node. So that is how it is connected. So this connection, this interconnection which is in between, which is shown in deep blue, this is generally some sort of a networking. Like some people, some systems use Ethernet, some even faster fiber connections. It has to be quite fast because while doing calculations, this node has to communicate to this node for some data. It might have to do some reduction through some other node and things like that. So this communication has to be very fast, and therefore major part of research, I think, in CS and all these things is to see, and a lot of companies are bringing out faster and faster interconnects which can improve the connection between nodes. So this also has to be very fast. Okay. Again, I have shown a simple connection topology. It is probably not always as simple as this. So there could be other network topologies like ring and things like that. That again depends on what type of a cluster you are building. Okay, so what are the features of this? Each node has its own memory. Each node in itself is a shared memory system. Like this system in itself is one self-contained unit. Each processor in a node can view only its local data. That is what we just saw in the case of what is called the shared memory model, that whatever is inside a single node is visible to all the processors, all the cores inside that node. Now the question comes, when remote data, by what I mean remote data? Remote data is something, let's say a node here is trying to get some data which is in the other node. Let's say some result of a calculation, it needs to process something in this node. So it has to do using direct message passing. This message is a technical term, and it comes like there is a whole protocol known as the message passing interface, MPI, which is used in these cases. And direct message passing, like you will pass the whole array or you will pass the whole list of variables as a message from one node to the other to transfer the data. That is again very expensive. By expensive, I mean, again, it is expensive in terms of cost also because it has to be very fast, and it is you have to use very high sophisticated networking, and also expensive in terms of time, because whatever it is, you are never going to be able to match the speed of the interconnect or the processing inside a CPU. So what will happen is CPU will be waiting for messages to be passed from one node to the other, and that will waste CPU cycles. So it is expensive in terms of time as well. Nevertheless, this is very common, as I said, in clusters and supercomputers with hundreds and thousands of individual nodes, because you need that many nodes, otherwise you cannot solve your problem. So it is very commonly used. It is seen in every cluster which you have probably in your institutes. The pictures I showed yesterday of some rack, those are again connected with some sort of a networking, and that implements this distributed memory model. That is one of them. Anyone, any questions and doubts regarding this distributed memory model? Okay, I will go forward. Now we come to the heterogeneous memory model. What do I mean by heterogeneous? So in general, if we come back to the shared memory model or to this one, all the memory I am talking about is system memory, as in RAM. Like whatever CPU you have, some RAM is connected to it, and they are talking between themselves, they are talking between different nodes and things like that. So that is more or less homogeneous. You will use the same sort of RAM across your system. You might have DDR4, DDR5, you might have 16 GB, 32 GB, 128 GB, whatever it is. It is homogeneous more or less across the whole system. What is heterogeneous is about here is, let's say you have a GPU. Last day we saw what is a GPU. It is a separate card. It is a separate card either in PCIe form or in SXM form, which is connected to the node. You can have one, you can have multiple. I think somebody was yesterday asking what if we have multiple GPUs also, that can also be connected. The difference is the type of memory you have in your CPU and RAM, that is generally different from what you have in your GPU. First, it is that. Secondly, it is separately attached as a card, like it will be put into a PCIe slot. So what happens, that memory is actually different. That is not in any way connected to this interconnect directly. It is connected, but through something like a PCIe slot. So this is a distinct form of memory. Therefore, it is called heterogeneous. There is RAM, which is here, and there is a GPU or multiple GPUs, which are connected here. And therefore, it is a heterogeneous memory model. Like you have two different types of memory. One thing, if you notice, while drawing the diagram, I have shown some cores here in light green, core 1, core 2, core 3. This GPU also I have shown memory in some light blue, and the cores, I have shown many cores. Because generally in a GPU, there are many thousands of cores, so that is what is represented here. These boxes represent the cores. So what we saw, GPUs have memory on device. So they come with their own memory. So if you have a GPU card, that will have memory inbuilt to it. You don't generally have to put memory into a GPU card separately. Whereas in a CPU system only, you have to put your memory like RAM. But it is completely separate from system memory, which is RAM. As we discussed, that is not connected directly. And the part which is the interesting and important part here is GPU memory is not directly addressable by the CPU and vice versa. What do I mean by this? Well, what we saw in the shared and distributed memory model, that the RAM, which is connected here, is directly addressable by the CPU. So this core can directly address memory here. This core can directly address memory in some other part of the system, and things like that. It is not directly addressable. The memory here is not directly addressable by the CPU directly here. Similarly, GPU cannot directly access memory which is stored in RAM. Some variable, some array you have stored in RAM, the GPU cannot directly address it. So it goes both ways. CPU cannot access and GPU also cannot access directly. Therefore, let's say you have to do a computation on the GPU in these light green color codes which I have marked here, but the data is initially in the memory here or here. There has to be a copying. So there is a connection. It's not like it is a separate device. Otherwise, it would make no sense to have such a card. There is obviously a connection through PCIe. So it has to be an explicitly copying of the data from this memory. That data has to be copied into this memory. Only then these cores can directly access this memory and run whatever has to be run. Whatever computation has to be run, it is directly run on using this memory. This course will not directly go into this memory to do the computation. And this data transfer is primarily the programmer's responsibility. What I mean by that is, if you don't do the data transfer properly, you will get wrong answers. Let's say you have an array in this memory which is like 1, 2, 3, and 4. You want to take the sum of elements of the array which is stored in this memory, which I'm pointing to here. And you want to use the GPU to compute that sum. But in this memory, there is another array which is like 5, 6, 7, and 8. If you just simply launch the kernel, the programs on GPUs are called kernels. We'll come to it later maybe. If you just simply launch the kernel using the array in this memory and you have not properly copied this, you will get garbage results. Sometimes what will happen is there would be no array inside this memory at all. So that time there will be a seg fault and it will crash and bad things will happen. Your program will crash and things like that. So before running some kernel, before launching some loop or some program inside the GPU, the memory which you need, the data which you need for the calculation has to be explicitly computed and transferred to the memory of the GPU. Similarly, after you have done the calculation, you want to do some other serial calculation. The serial calculation cannot be done by the GPU. It has to be done, I think, on the CPU only. That way, then again, you just simply cannot start doing the calculation assuming this will appear on the RAM magically. It has to be copied using some command through the PCI Express connection into that memory, and only then you can do the computation on the CPU. So it is primarily the programmer's responsibility. There are compilers which will do it for you. So we will see, like next day when we see the compiler, the PG compiler and all that, they have options which can actually do this, because compilers are quite intelligent. They can do this data copy. They will look at your code and they will try to do the data copy for you. But they are not very intelligent. So if you leave it up to the compilers, they will do something. You will get the correct answer. But what happens is this, again, it becomes a question of a bottleneck of copying data. If you are copying huge amounts of array from here to there, from this CPU to GPU and GPU to CPU and back, if you do that too many times, you will be losing performance. So you have to intelligently see what data copy can be done so that you can reduce the amount of such copies. Like you have to do it once or twice during the whole computation. Otherwise, this copying will become too much and you will again have a slowdown rather than having a speed up. So it is primarily your responsibility as a programmer to find out what is the best way of copying data. This is why in beginning I said data is king. Like you have to be very careful how you are moving your data. Your program might give correct results, but if you have not optimized the data movement, that would mean you will actually get bad performance. It might even become slower. We will come to such examples in the next week's class where we solve some PDEs or ODEs. If we don't optimize the data movement, your performance will be even slower than a CPU. Okay, anybody has questions from this heterogeneous part of the discussion? Okay, so yeah. Again, I have shown an example with one GPU here. There can be multiple GPUs. That way you have to be able to control data transfer to multiple GPUs as well. We will probably see some examples while we are doing some coding in the next week. So now we have a complete picture. A typical cluster will probably look something like this. It will have an interconnect in between. Excuse me once. It will have an interconnect in between, and through the interconnect, many such nodes will be connected. Each node will have some X number of CPUs with many cores and memory, and some of the nodes over here, I have shown all the nodes having a GPU, but then in that case, some of the nodes might have a GPU, some of the nodes might not have a GPU. So that is how a cluster will be configured. For example, the cluster in IIT Madras, it has, I think, only 30 nodes which have GPU, something like that. So not all nodes will have GPUs. So, I mean, I have drawn it like that, but okay. Yeah, and you will have to select which node you have to use and then run your jobs. Okay, so this is more or less the complete picture of what a cluster would look like in terms of the memory and CPUs and GPUs. Okay, so this is the more or less the three different memory models which is used, and this is the complete picture coming out of it. Now we know something about the memory, how the memory is arranged within such a node, cluster and a GPU, things like that. Now comes the question of how will you program it. As I have said yesterday, you cannot simply take a serial code, you write some program in serial, you cannot directly expect it to run on a multi-core GPU or a multi-core CPU and expect it to utilize it properly. It will run, it will definitely run, but what will happen is it will go to one of the nodes and just take one core of it and run on that. So that way it is not using what is available in the whole cluster or in the whole node. So there has to be some programming model, a way to tell the computer to run your program on different nodes, different cores. So we will come to that. For the shared memory model, where typically there is a single node with one or more CPUs, the shared memory model we just discussed, which has a single node and many CPUs with multiple cores inside, you can use something called OpenMP, and you can use OpenACC using the target architecture of multi-core. This is one of the reasons we are going to do OpenACC. It can be used for GPU execution, and it can be used for with some compile time flag, it can be changed using the same code. You don't have to change the program inside. What you have written will remain the same. You just change one flag during compilation, and it will run either on the GPU or on the CPU depending upon what flag you give. OpenMP is one of the standards which is used for parallelization only on CPU. That was still, I think, version 4. From version 4, OpenMP has included GPU support, but it is probably not that mature as OpenACC. OpenACC is maintained by NVIDIA. They've sponsored the project, something like that, and they have access to everything and their output, and it is quite a mature platform. We will look into it in the coming weeks about OpenACC. So you can use either OpenMP or OpenACC to do programming on a shared memory model system, like a single node with multiple CPUs. It does not need to be multiple CPUs. In your laptop also, you can use OpenMP and OpenACC, so that whatever 6 cores or 12 cores you have in your laptop, you can program on that. For the distributed memory model, where there are multiple such nodes, like we discussed a few minutes back, you have to use something called MPI. That is called the message passing interface. As I said at that time, there is explicit passing of messages. You have a node here, you have a node here connected in the network. This node has to explicitly pass a message with all the variable information and your arrays and whatever you need from this node to this node, if this node has to use in that computation. So it is a message passing has to be done, and therefore MPI is used, which is called the message passing interface. And in case of heterogeneous memory, like you have GPU in it or things like that, there are again many options. The option which comes to mind directly is CUDA. You have probably heard the name. It is for NVIDIA GPUs only. It is their proprietary stack in which you have all sorts of libraries and ways to program the GPU, but it is for NVIDIA only. OpenACC is again maintained by NVIDIA, but it has probably some support for other company GPUs as well, but it is very limited. So you can call it for NVIDIA almost only. OpenMP from version 4.0 has an option for offloading to GPUs. What is meant by offloading? That some portion of the code will be sent to GPU for execution. That is what is meant by the terminology offloading. So some portion of it is computed in the CPU, some portion of it is offloaded to the GPU. So OpenMP has added support for that from version 4. And there are other options on like OpenCL and SYCL. SYCL is probably made by Intel. I think there was another NSM course which was going on a few days ago on SYCL. It is probably pronounced SYCL. So this is how These are the many ways in which you can program heterogeneous memory devices like nodes with GPUs. If you remember, few days ago, the last class, we discussed something called an FPGA. So if you have to program an FPGA, OpenCL is an option. So, okay, SYCL is by the Kronos group. Okay, thank you for the information. Yeah, okay. So, okay. So OpenCL can be used to program, I think, FPGAs, and SYCL is also probably used for programming FPGAs as well. I am not quite knowledgeable on this part, but yeah, those can also be used to program GPUs as well. But predominantly the industry, the market leader in this case is NVIDIA, and therefore CUDA is used a lot, and OpenACC is also used for programming. This is if you have to program your own algorithms and own some algorithm you are coming up with, you have to program that, you will be using one of this. Otherwise, let's say you simply want a function, you just want to do a matrix multiplication, you want to just generate random numbers, you want to do some BLAS operations, matrix multiplication is a BLAS operation, you want to do a tensor operation and things like that, you can use pre-existing libraries. C++ libraries like it as part of the CUDA toolkit, you will get cuBLAS, cuRAND, cuTensor. They have recently added cuQuantum, like if you want to do some quantum mechanical calculations like evolution of the state variables and things like that, there is a library called cuQuantum and a lot of things. So there are pre-existing libraries. These are pre-existing as in you cannot modify them. If you have to write your own low-level code so that you can write your own algorithm, you have to use one of these things. And for GPU, you have to either use CUDA or OpenACC. If you are using Python, you are in luck. There are many libraries which are already written for GPUs. You can use CuPy, Numba, and things like that. Yeah. So CuPy, Numba, and there are other libraries. There are machine learning libraries, TensorFlow, and things like that, which already have GPU support inbuilt. So you don't have to worry about GPU in that case. You just directly you just call the function and it has been automatically written in such a way that it will run on the GPU. And there are other languages, like I have not mentioned it here. There are many other languages. One of the examples which come to mind is something called Julia. Julia is a programming language which is recently being developed. It has come out in probably 2014. It is still quite early days for it, but it has again inbuilt support and inbuilt libraries which can be used for GPU programming and parallel multi-core programming. So there are many options. So the takeaway from this is if you want to use predefined functions, you can use the libraries. If you have to write your own algorithms, you have to either go to some of these programming models like CUDA and OpenACC. Okay. So what is our plan? So from next week, we will do OpenACC. We will start with how to install OpenACC and how to write your first Hello World program, if you call it. And we also need a little bit of OpenMP. Why do we need OpenMP? First of all, OpenMP is only for running on the CPU. They have used, as I said, introduced GPU, but primarily it was developed for that, for CPU parallelization. And it is very syntactically similar to OpenACC. Both use something called pragmas. What are pragmas? Pragmas are compiler directive. You write hash pragma in C, or I think in Fortran it is like you give a exclamation mark pragma. I'm not sure about the Fortran syntax, but in C what you do is you write hash pragma OMP parallel. Similarly for OpenACC, you do exactly the same thing. You write hash pragma ACC. Not OpenMP, you write OMP. In this OpenACC, you write hash pragma ACC. So both use pragmas. They are syntactically very similar. If you look at two codes, one written using OpenMP and using OpenACC, they will look very similar. Apart from small things, like you don't need to do explicit memory management in OpenMP if you are trying to write code which is for parallel execution on the CPU. But other than that, OpenACC and OpenMP looks very similar. Again, they follow the similar execution / control flow, but again, they are not exactly the same, but very similar. And in the course outline, you will see there is a small topic of multi-GPU programming. Multi-GPU is like if you have multiple GPUs, like in my system, I had two RTX 3090 GPUs. To control such a multi-GPU system, you will require a bit of OpenMP. And again, OpenMP itself has GPU uploading support. Although we won't use it, but it might be useful because it is still a developing thing and not all compilers have enabled it. But it is the hope that OpenMP, if it is possible, that they will also properly include GPU uploading support into it. And again, it is very simple to learn, and I think everybody should know CPU parallelization techniques a little bit. It will actually help you thinking about GPU parallelization as well later on, let's say while using OpenACC. So right now we will probably look into a bit of OpenMP. As I said, let's say we have around 15 to 20 minutes time. So we will look into a bit of OpenMP, and from next week we will start OpenACC. This week we will end this initialization and the introduction to parallelization part, and I thought it will be well to do a bit of CPU parallelization so that you start thinking about problems parallelly. Like directly, if you want to think about GPU parallelization, it becomes a bit difficult. But once you start slowly thinking about how you will do it on the CPU, then you can translate the same code into how you will do it on the GPU. So that's why I have decided like we should look into a bit of CPU parallelization using OpenMP. All right, so this is the OpenMP execution model. It is called a fork join model. What do I mean by that? This is very important to see because OpenACC will also follow a very similar thing. Excuse me. Again, if you remember the example I had given yesterday regarding parallelization, there was parallel task 1, parallel task 2, and parallel task 3. In my example, I had just used color boxes. Here they have given ABC, ABCD, AB, and whatnot. The top thing is for if you have a serial execution. The tasks are parallel, but since you are executing serially, they will be executed one by one in sequence, and it is executed by what is called the master thread. What is meant by the master thread? Like every program, when it starts, like you are running the program for the first time, you are doing /. In Linux, you do / program name, and you pass some variables or you just run it. It always starts with the master thread. The master thread starts executing the int main, like it will start at int main, right? That will be started to execute using the master thread. And if it is serial, it will execute all the programs, all the parts of the work one by one as shown here. In the fork join model, when you are doing OpenMP, again, we will start with somebody is asking, does OpenACC work with multi-node, multi-GPUs setup like a cluster? No. So if you have multi-node, what you have to do is you have to use MPI. Multi-GPU you can do using OpenMP and OpenACC, or probably directly using only OpenACC. But if you have to do multi-node, you have to use something like MPI. Does that answer your question, GK? Okay, I hope it does. Anyway, I'll go ahead with this. So yeah, so fork join model is like there is some set of parallel tasks. You launch a master thread which starts executing from int main, and you first encounter the first parallel region where it forks. You see what they have done? There is one master thread coming, and it has then forked into 3 child threads or 3 child threads here. What? Because they have 3 tasks which have to be executed in parallel. They have forked into that. So it is called the fork. At this point, it is forking, and it is going to execute all the 3 jobs in parallel, depending on what is the number of tasks you have and the number of CPUs you have available in your machine. It will execute it in parallel. So over here they have shown up example with 3. So the master thread executes A, and 2 child threads execute B and C. When that is done, it joins at this point. After it finishes parallel task 1, it joins here. That is why the fork join model comes. This is called the fork part. This is where it joins. Then again, this part you have shown empty, but this part might contain some other serial tasks. Like, let's say you have to do some other serial task which you cannot do in parallel. So that might be done between these two parts over here. Then again, you end up in another parallel task. Over here, they have shown 4. So again, master thread takes up 1, and there are 3 child threads which take up the next 3. Okay. So this is basically, they complete, again, they join here. And again, the final parallel task, again, they fork here and join here and they end. So this is basically the fork join model. This is, you will launch parallel sections within serial parts. So these are parallel sections which are mixed with certain serial parts of the code. So for example, if I give you some example of this, it would be like, let's see. Okay, it has to be something like you will do some shopping and you will bring some food items to your house. Then everything has to be washed, and that washing process is again a parallel. Like if different food items can be washed in parallel. Then maybe you have to mix them together, marinate them and all that. That can also be done in parallel. But then there could be some serial parts of it, like you have to first cook one part, only then you can mix in with some other parts. So you can have like different examples. You can, I think of other examples as well, where you can mix up serial and parallel parts of the code. Okay, now let's look at some of the details. Like if you have a Linux system, you have to first install the OpenMP library. It is probably not directly installed fresh out of the box. Some distros do, but then if it is not installed, you can install it using sudo. I am using the apt package manager. If you have some different package manager, you have to use that, and sudo apt install libomp-dev. This is more or less the install command, at least on Linux, Mint, and Ubuntu. So if you are using those, it is pretty simple. The other thing is you have to use a header file in every C program on top. If you are going to use OpenMP, you should include #include omp.h. And while compiling the program in GCC or G++, you have to use a flag -f openmp. This is the flag which has to be used to tell the compiler to link that OMP library so that all your functions and everything works. So these are the 3 important points, like if you have to use it in your code. Now I will show first 2 examples before going on to something else. This is just one of the boilerplate code I had written to illustrate an example of how you can use OpenMP. So like a C program, you do stdio, math and all that. And you have to include this omp.h like I have included. Then you write your int main. Then over here, you will have your sequential code. Something you have to do, maybe initialization and things like that. Then what you write is to launch a parallel version, like to launch a parallel portion of the code. By parallel, I mean this parallel task 1 or parallel task 2 and things like that. You will write #pragma omp parallel. Whatever is inside these braces will be executed by n number of threads. What is this n? That you can control from the terminal, and it is generally equal to number of cores you have into 2. That is the number of threads. Let's say you have 6 cores. Therefore, you will probably run this part using 12 threads. If you have hyper-threading enabled or SMT, like AMD calls it. If not, you will execute it using 6 threads or 6 cores. So whatever you write within these 2 braces, that is executed by a parallel group of threads. Again, after that region ends, you can have serial code, and that will again be executed by the master thread. The master thread I was talking about there, that will execute the first sequential part of it. Then it will launch a parallel region which will execute using 6, 12, depending upon how many threads you have, how many cores you have. That is will executed using this parallel region, and then you again will go into sequential code. This is one way of doing it. The other thing is, people who have been programming for a certain amount of time, they will know that most of our work, especially in this numerical methods or in any physics or engineering problems, if you are from that background, you will know most of your work involves either arrays and loops. You will store a data in an array, you will store some position, some momentum, some spin, things like that, probably in an array, and you will write a for loop which will go over each element of that array and do some operation into it. For example, the example I have shown here is of something like a vector addition. So your vector A is one of the vectors of length n, B is another vector of length n, and you are directly doing a vector addition and you are producing a vector C. This is a very common example in some numerical methods or in some physics or engineering problem to do a vector addition. So the shortcut way of writing this, whatever parallel version of it, is to write something like hash pragma OMP parallel for. So what it will do is, your compiler will automatically generate code which will launch some k number of threads. It is not always that if you have n here in the loop, that n will always be the number of threads you will get. Your n could be 10,000, 100,000, 1 lakh, 10 crores, you don't know. But you don't have that many cores in your system. So it will launch it with how many number of threads or cores it has available to it in some scheduled manner. So it might do round robin, it might do dynamic allocation. Those are more internal details which are important, but right now we don't need it. I will maybe show some examples a bit later on, but it will have some scheduling. If n is quite large and you have, let's say, 10 threads, you cannot launch some 10,000 threads directly. So there will be some scheduling, and that scheduling will be used to do this for loop in parallel. So maybe it will do it in batches of 10, it might do it in batches of something else in some other way. Yeah, so this is more or less how you will write basic OpenMP code. This is a direct parallel region, and this is what is called a work sharing. Like, this is some work that is being shared. So yeah, so for loops can be targeted for parallel execution using that's hash pragma OMP parallel for. And again, once you have this, you have to compile your program using GCC and G++ and use the -fopenmp flag. Okay, so these are the basic examples. Now what I will do is, since this is not a course on OpenMP, I will actually show you what is the OpenMP reference manual. So OpenMP is basically an organization. They will every year or every 2 years come out with an API. I think all of you know what an API is, a document type thing or a full thing where they have like shown whatever features they have in their system, like in their library and OpenMP. So I will go to that. So give me a second. So using that, maybe we can have a quick look at what features are there. Okay, so this you see is the OpenMP API, and it came version 5.1, August 2021. I think this is the most recent one. So it has been revised on August 2021. So if you look at this, I suggest each and every one of you in this week, maybe you should download this PDF. I will share it in the Google group and look through this. I have marked a few portions which I feel is important, like these are the basic portions which everyone should know regarding OpenMP and parallel programming. And this will again help you in your programming of GPU. So we will look at some of the examples which they have shown. Again, as I had said before, all this will work for both C++ and Fortran. So that both of that, if you are using Fortran, you can also use that. So first, let's look at, by the way, this document is very detailed. Like, there are a lot of things. You can look at program control, reduction, synchronization. This is one very important thing. Then, as I said, OpenMP has added support for GPUs as well. Therefore, a chapter called devices is also there. So yeah, we will see one or two examples from this. So first, let's go to this example. This is just a simple parallel loop, what I had shown there. So they are just doing, they are taking in n, they have defined a function simple, they are taking n, and they are taking two arrays. It has been passed as a pointer. And what they are doing is, they are running a for loop for I equals to 1 to n, and for every element b of I is being updated with a of I plus a of I minus 1. So they are taking two adjacent elements and adding it and dividing it by 2. So again, it becomes an important question here to identify a parallel example. Like this example which they have shown here. It is something like a Fibonacci example, right? You add the two previous things and you get the next number. Something like Fibonacci, but not exactly that. You have divided by 2 and all that. But anyway, so for every iteration I is independent of whatever iteration is coming before it. So let's say if I is 1, this will be like b of 1 is a of 1 plus a of 0. You cannot do this if you have b on the right hand side. Let's say you have to use b on the right hand side to update b. Like if I gave here b of I is a of I plus b of I minus 1. Let's say this a is not a but b. I'm just giving an example. In that case, you cannot do a OMP parallel for. Can somebody tell me why?
Because further values of b are dependent upon the previous values of b.
Exactly. So what he is saying is correct, that if you have dependence on the values of b, you cannot actually use parallel for here. You can only use it here because both sides, in this side you have only b and it is of iteration I, and that depends on a. If again in this loop you are modifying a, let's say again this is not a single line loop and you have some loop which is going like a of I is something something. They have not written yet, but I'm saying let's have a of I is equals to something here and there is some update. Again, at that point you cannot do that because you are using a of I and that a of I is again getting updated inside this loop. In that scenario, you cannot use a parallel loop. And this same example carries over to your GPU programming as well. If you are going to write a loop like this is fine. This will again run properly on the GPU. But if you have B here or you have an update on A here, you cannot write that type of a loop on GPU as well. That is why I said it is probably a good idea to look into how CPU parallelization also works. All right. One comment here is the variable I is private by default. What that means is each and every thread, let's say they launch 5 threads here to do n iteration. Every thread will have its own private value of I. What do I mean by that? If I just go back to that slide, in this parallel region, I'll just zoom this in. In this parallel region, there is individual memory allocated to each and every one of these threads. There is some private memory. Each value of I will have a value particular to that I value only. So this I, let's say, is like 0 because generally master thread is 0, thread num. This will be 1, this will be 2, and similarly, the value of I will also change thread to thread. So that is what is meant by is private by default.
Why is there another for loop in Pragma op OMP parallel for? Like, is
Yes.
it supposed to be a for loop or what?
Yes. So it is like you can write it in two ways. I will show you probably one example. You can write it, this is just a matter of syntax. You can write it hash pragma OMP parallel, and within that again to do for loop, to do this parallelization, you have to again write hash pragma OMP for. Okay, so that can be just written simply in a single line using hash pragma OMP parallel for. That answers your question?
So the 4 here signifies that this following sequence is going to be parallel.
This for, are you talking about this thing?
Yes, yes.
This implies that the statement following it is a for loop. It will be expecting a for loop immediately after it.
Okay.
All right.
So like if there's some like a while loop, we should write while there.
In let me see. I don't think you can parallelize while loops in C, because in while loops there is no fixed number of iterations. For loops are generally written with fixed iteration numbers, right?
Right.
So right. So yeah, that way you cannot actually parallelize while loops that way. That can be done in some other roundabout way. Maybe we can discuss that later. So, but then it will be exactly following something. It will be expecting a for loop to come after it.
Okay.
Yeah. Again, that was one example. The other example is probably over here. Yeah, that was a for loop they have shown, and now they are showing an example which is just using a parallel region. So what does it mean? It is not going to launch any loop. It is going to just launch some n number of threads. Okay. So in that case, they are doing some computation. How they are doing it, what is important is, let's say, what becomes important here is, let's say you have 100 iterations to do and you get only 5 threads. So again, you have to do it using chunks of 5, each 100 of them, right? So you see, OMP get thread num is a function which will tell you within the parallel region what is your thread number. Each thread gets a number. Okay, master thread is 0, and and you have n-1 child threads. So if we total have n threads, you have n-1 child threads, and master thread is 0. And if you know that, and you know how many threads you have actually got, that is given by the function OMP get num threads. Using these two information, you can actually find out what is the partition size. Like if you have got 5 threads and you have to do 100 iterations, you will partition it into sizes of 5 and things like that. So this is one of the important things and how you do it. See, the important part, again, another thing is you have to think in a parallel way. Like you will have execution in parallel. So you have to think how using that thread index, that is also called thread index, how using the thread index, you can do whatever computation you have to do. Let's go to some other example as well. Yeah, let's see this parallel sections. So again, it is like hash pragma OMP parallel sections. In the other case, it was for. Now they are writing sections. What happens is, inside this bracket, there are hash pragma OMP section, different sections are there. Each thread will be, so let's say you get 3 threads here. One thread will execute the first one, the other thread will execute the second one, and the last one will be executed by the third thread. So that way you can divide. So let's say you have 3 different functions you want to call in parallel: x-axis, y-axis, z-axis, what the example they have given. That way this will execute in parallel with this and in parallel with this. So this is another way of calling multiple functions in parallel. Okay, and yeah, you can look at this also. Okay, the question he was asking, like, why was there a loop here? You can actually do it something like hash pragma OMP for or hash pragma OMP loop, and you can use this as a like, you can put it here, or this is a shorter way of, the previous one was a shorter way of writing it. I think there are few more examples, but I think we are just out of time. It's 3 o'clock. I would suggest I will share this PDF and I have marked certain sections. It is not very important, but I would suggest you just to look at it and try to understand what is happening. Like I have given you a basic understanding how parallel regions are launched and how a parallel loop will be launched, because in OpenACC we will be mostly using loops. There will be certain other clauses as well, but we'll be mostly using loops. So I would at least suggest you look at how loops and parallel constructs work. I think this is enough for today. It's already 3 o'clock. Maybe I can take a few questions before I close the presentation. Okay, let me see some questions. The official website for this course is down. Can you look into that? Okay, I will see. And Ronak says, could a parallel program, one sec. Let me just stop the screen sharing once. Yeah, could a parallel program be run on computing a sum of all the values of array? Yeah, so you can do that, but what you have to do is called a reduction. So I will come to that during OpenACC. And also maybe you can look at it in this document which I will share, that is called a reduction. But yes, you can do that. A parallel program can do a sum. Ronak, does it answer your question? Okay. All right. If there are no other questions, maybe I'll just stop the recording here. Recording stop.